to come on stage and start the session. Thank you.
Hello, everyone. Welcome to the last session of the day. And the first talk is going to be by Saurav, who will talk about discovery of Higgs boson at the Large Hadron Collider in CERN. Oh no, the first talk is by Sunanda Banerjee, and he will talk about discovery of Higgs boson at the Large Hadron Collider in CERN. Sorry.
So I have to. Oh, this is the. It's yours.
No.
Okay.
Higgs boson discovery. It was on this.
It's on my laptop. I think.
Oh, acha, you changed.
You have to change. Yeah, so I have to change this laptop.
আপনি আপনার টক ছিল এই সময় নাকি
Exactly.
অ্যাকচুয়ালি আমার সব শিডিউল ছিল পরশু দিন আমি পরশু দিন
It doesn't matter.
Okay, I'll start this one.
কোন দিকে যাবে
Okay. আচ্ছা এইটা চলে গেল
ল্যাপটপ না ই করছিল ওইভাবে না
এটা বন্ধ করে আর একটা চেঞ্জ করছি
1 মিনিট ল্যাপটপটা আমি করতেছি অফ হয়ে গেছে ল্যাপটপটা মানে শাটার ই করছিল পুরো ই হয়ে গেছে স্লিপ করে চলে গেছে এটা অন অফ করে অন করতে হবে আর হবে এখন অন হচ্ছে দিও না ওয়েট
আচ্ছা এটা রিস্টার্ট
হ্যাঁ হ্যাঁ ওই মানে শাটার দিলে হয় কি স্লিপ করে চলে যায়
এটা স্টার্ট হচ্ছে ঠিক আছে পাওয়ার আছে
আর মানে আরেকটা ল্যাপটপ দিলে হবে না পেন হ্যাঁ একটা ল্যাপটপ এটা আবার ইয়ে করবে তো আবার এটা স্টার্ট হবে রিস্টার্ট এই যে
এরকম হচ্ছে কেন?
ল্যাপটপ আরেকটা স্যার আনছিল, এটা মানে ই করছে, শাটার ই করছে, পরে স্লিপ করে চলে গেছে।
এই ব্রেকের মধ্যে করা যেত না?
না না, এটা এই মাত্র
কি রিট্রিভিং? আরেকটা ল্যাপটপ দেবো নাকি? বারবার এটা করতে থাকবে। হুম?
ল্যাপটপ।
হতেই থাকবে।
হয়েছে
বন্ধ? হ্যাঁ?
হয়েছিল, ওই নেট কালেকশন করা ছিল স্যার, অনেকে ওই মেইলে দিছে, হোয়াটসঅ্যাপে দিছে, এই জন্য অটো আপডেটটা নিচ্ছে।
এটা খালি বারবার অন হচ্ছে আর অফ হচ্ছে।
আমি ডাটাটা অফ করে দিয়েছি, ডাটাটা অফ ছিল এর জন্য হয়েছে।
আর ওনার না কি ওনার নিজের?
এটা কার?
আমাদের
আচ্ছা,
এই যে আসছে।
আর আমি ডাটাটা অফ করি, ডাটাটা অফ করার জন্য এই রেজিস্টার নিয়েছি। নিতে না,
ডাটাটা অফ মানে কি? ডাটা কি?
ওই অনেকে মেইলে দিছে, ওই প্রেজেন্টেশন অনেকে হোয়াটসঅ্যাপ দিছে, তখন তো এই ডাটা কন্টিনিউ অফ অন ছিল।
মানে বাইক করতে তাড়াতাড়ি?
হ্যাঁ।
হ্যাঁ।
লাগবে?
না এখন লাগবে না।
HDMI দাও।
ওখান থেকেই করবে?
হ্যাঁ, না ওখানে গেলে সুইচিং করবো, অনেকের পাওয়া আর কিছু না।
ওটা সুইচ করে দেয়।
আমার
ওই
তো
হয়ে গেছে।
লোড করা আছে।
হ্যাঁ হ্যাঁ হ্যাঁ, সব
হয়ে গেছে?
হ্যাঁ হয়ে গেছে।
ওকে ওকে
Fine.
ফাইন। আচ্ছা আমার টকটা আমি দেখলাম না, ঠিকই আছে।
আচ্ছা আপনি ওই দিয়ে রাখলে এখানে সব আছে।
হ্যাঁ, এখানে আছে। হ্যাঁ,
হ্যাঁ,
যেটা আগে ছিল সেটাই।
হ্যাঁ হ্যাঁ হ্যাঁ, ডেস্কটপে সব আছে, সমস্যা নেই।
এই ফুল স্ক্রিন করে দিয়া, ফুল স্ক্রিন করে দিয়া। হ্যাঁ ঠিক আছে।
Let me start by thanking the organizers, okay, for inviting me here. I go to this conference for two reasons. Though I am from Calcutta, okay, my mother comes from this part of the thing, okay, I mean, not Dhaka itself, but from Sylhet. The other thing is the picture of this gentleman who is being shown here. He happened to be a classmate of my grandfather. I mean, my grandfather studied also from Presidency College, Calcutta, in mathematics and physics in the same year with Meghna Shah and Shatyen Bose. And we had a picture of the whole class, okay, in my grandfather's place, okay, I mean, and that was my biggest treasure for many years, okay, I mean, before I really left Calcutta and went out of that. So with that, let me start on something, okay, where I come in, and that was in the discovery of the Higgs boson. This is a curiosity of the human mankind. They have to look for the fundamental constituents of matter almost from the beginning of civilization. And the thoughts which came to both the Western world and the Eastern world, they were looking with the same 4 or 5 fundamental constituents from which everything can be built of. So these were the fire, earth, water, air, and the fifth one, which is sky, okay, which was added from the eastern side. Now, modern science, I would say, started around the 16th century, and there any postulation which was made from the human mind, they needed to have an experimental verification. And this gentleman over here, okay, who is Galileo Galilei, he made a statement, I attach more value to finding a fact, even about the slightest thing, than to long disputation about the greatest questions that fail to lead to any truth whatsoever. Today we address the greatest questions through experimental verification. What we normally say, okay, which you have is essentially nothing but a postulate which comes to the human mind, and without an experimental verification, this is not a theory. So till the end of the 19th century, this search for the fundamental particle was done mostly in the domain of chemistry. So the idea of compounds, elements, the classification of elements in the periodic table, the idea of molecules and atoms, all these things, okay, were fundamental constituents of chemistry. The conclusion that all matters were built out of electrically neutral units, atoms of several fundamental elements. On the physics front, the investigation was on for the types of interactions among matters. There are only two interactions which are known at that time, the gravitational interaction between any two objects having mass, and the electromagnetic interaction between any two objects having an electric charge. So this was the story at the end of 19th century, and essentially there was a revolution just around the corner during the end of 19th century when this field became the working area of physicists. This came through the discovery of electrons, radioactivity, nucleus, and so on and so forth, which really revolutionized the area of science. So during the 20th century, with the discovery of accelerators, many modern techniques and detecting basic constituents and their interactions, people came up with the idea of a new zoo of fundamental constituents. This has been said by many people in the previous lectures in this conference. We have a group of spin-half particles exhibiting Fermi-Dirac statistics, make up of all the constituents of matter. And these particles interact among themselves through the exchange of some spin-1 objects exhibiting different statistics, and that is where SN Bose comes in, okay, with this Bose-Einstein statistics, and that is called bosons. Now, it's not just the particles which were different, we also had new types of interactions, and there are two new types of interactions which are there. One is called a strong, which puts the nucleus together, and the other is weak, through which the radiative decay comes in. And they all could be explained through a theory which is called the quantum field theory, and this gave birth to the standard model. Okay, obviously this was a model, you can see, okay, it's not a theory as such, it was called a standard model, and this model has very good high energy behavior. So this is what we have, a zoo of particles. You can see, okay, the particles over here, okay, these are the things which have got the spin half, okay, these are the, I can't really show it here. These are the spin half things, and you have got something in color. That means, okay, these are the quarks which comes in 6 varieties, okay, we call 6 flavors and 3 colors. And similarly, okay, we have got leptons, okay, which comes in, okay, again in 3 varieties. And you have also what you call the left rotating neutrinos and the left rotating objects and the right rotating objects. But this is not everything, except, okay, you have to introduce a non-zero masses for particles and keep the good high energy behavior. So this was a puzzle before, okay, these 6 gentlemen, okay, you can see, okay, from left to right, Guralnik, Hagen, Kibble, Higgs, Engler and Braut, they came up with a theory, and this theory, okay, I mean, could introduce by some means, okay, I mean, a mass of this particle without breaking the high energy behavior of this theory. Now, one of these gentlemen, okay, I mean, one of the 6 gentlemen, he said, okay, if this such a theory exists, there should be a particle of special type, and this particle of special type is a spinless particle, and this is definitely a new species altogether, and the goodness of this particular model or this particular theory can be proven if you find this Higgs particle, we already call it Higgs boson, okay, if you find this or not. Now, obviously, okay, I mean, if you say, okay, there's such particle exists, how can you look for it? If you are given a name and you try to say, okay, you try to find it in a city like this, okay, I mean, I'm not to say, okay, which city it is. It could be Kolkata, it could be Dhaka. But if a city like this, okay, and you say, okay, I mean, you try to find, okay, that particular person, how will you look for it? It's almost impossible to find a particle in a city of 20 millions and no address whatsoever. So we had to really find an address. And I'd go back a little bit. During the second half of last century, there was a focus of designing experiments to find the predecessing particles, the W bosons and the Z bosons, and measure the properties with very high precisions, and also to look for the 6th quark flavor. This is an accelerator which was built in the Swiss-French border. It is called CERN. I mean, the whole thing was situated some 50 meters underneath the Earth and had a circumference of 27 kilometers. This experiment, the management of this laboratory, CERN, they had a discussion in the 70s to construct this thing, okay, to look for, essentially to look for the W and Z bosons. But there's one gentleman who came in who was quite clever. He said, okay, why we wait for this? We can use the existing accelerator, which is, you see the smaller circle over there. This is called the superproton synchrotron. We can use the superproton synchrotrons and we collide protons against antiprotons at sufficiently high energy, and they did an experiment to observe both W bosons and Z bosons. But they could not measure the properties of either the W bosons or Z bosons with sufficient precision. So the lab was engaged essentially to measure the properties on Ws and Z bosons, and also they tried to look for Higgs bosons for the first time in a more, what you call, model-independent way, and they could not find anything, okay, and they said, okay, I mean, there is no Higgs boson as expected from the so-called standard model of mass with mass below 114 GeV. So they now came again, okay, the idea of theoreticians, and what they said, okay, I mean, if you do not observe the particles directly, if you make a precise enough experiment, you can indirectly see the effect of those particles. For example, when you look for interactions of electrons and positrons to produce hadrons or leptons in the final state, normally, if you measure the probability of this process very, very accurately, you can see the effect of heavier objects, and this is called radiative corrections to do that. So this particular method was deployed in lab, and what they saw is that, okay, before the top was discovered, they said, okay, if top exists, it has to have a mass in this particular yellow band on the left plot over here. Now, you can see, okay, I mean, somewhere around 1995, top was seen, and you can see that the mass of the top quark was just within this yellow band. So this is possible essentially due to this precise measurements and accurate theoretical calculations. I think these two gentlemen, Tuft and Weltman, got a Nobel Prize, okay, I mean, when this was proven. And obviously, okay, it's not just the top quark. Higgs also has got, okay, I mean, can be produced, okay, I mean, there could be a prediction on the Higgs boson mass using in the standard model framework. And the top right plot, that is shows, okay, the mass region where Higgs boson is expected. Okay, so we know, okay, I mean, Higgs boson, if it exists in standard model, should have a mass somewhere between 100 GeV and 200 GeV. So these are the indirect hints. So now how to find Higgs boson? Okay, so again, we took the help of theoreticians. These are the two theoreticians working at CERN. Okay, this is John Ellis and Marie Gaillard. And they tried to work out, okay, I mean, all the production processes of the Higgs bosons. So we collide particles with sufficient high energy, and protons are a good choice for colliding particles, and the probability of Higgs production is small, so you need a very large number of interactions. So they also tried to look how the Higgs boson can decay, and depending on the mass of the Higgs boson, okay, it can decay to very many types of final states. Okay, it can decay to a pair of photons, it can decay to a pair of four leptons on two leptons and two quarks, and so on and so forth. So we try to look for all possible signatures, and observation of a multiple final states can only establish a new object. So this was the approach which was taken, and we went and tried to have this proton-proton collider which was built in CERN, and this was completed by about 2008 or 2009. The accelerate of beams of protons almost to a speed of 99 point, you can see, okay, I mean 5 nines after point decimal percentage of the speed of light. So it is incredibly high speed, they are being accelerated and they collide against each other. Now this CERN is, what do you call, what's the word? They are rather stingy. That means, okay, they try to utilize, okay, all the old products, okay, I mean, try to build this thing. So long ago, okay, I mean, the proton synchrotron, which is seen is called PS, that was built at CERN in the 50s. Then in the early 70s, okay, they have the superproton synchrotron, which was built. So they utilized all these components of these accelerators, and they finally built this 27-kilometer tunnel in 1989. And so they completed the whole construction, but at the beginning, okay, it was injecting only electrons and positrons, but they have to inject protons, and these protons, as I said, okay, has to go at a very high momentum, so obviously they have to put this very special type of magnets, okay, to keep them in this orbit. So you have got as I said, okay, we need a large number of these interactions so that, okay, we can see this thing. So these are the basic properties of this thing, but the whole point is that we have to collide protons against protons, where the beam size is like 15 micron by 15 micron, and they are collide at a rate, okay, at something like about 40 megahertz. And we have to photograph each of these interactions very fairly accurately, okay, to yield any results out of this. So what makes this Large Hadron Collider? So to contain beams of Large Hadron Collider, we need something like 1,200 odd dipole magnets, which are 15 meters long, and providing something like about 8.3 Tesla, and operated with a current strength of something like 11 to 12,000 ampere. So obviously, okay, I mean, if you have to have magnets operating at such a high current, you better try to get rid of the heat produced by it. So you need superconducting magnets are working at liquid helium temperature. To focus beams to tiny sizes, we have to have something like 400 quadruple magnets, which are again superconducting. And to accelerate and supply this lost energy, you need superconducting radio frequency cavities, providing something like about 4.8 megawatt. So we just have a few facts about LHC. The energy stored in the magnets is like 11 gigajoules, which is like an Airbus 380 at a cruise speed of 700 kilometers per hour, and it can hit and melt something like 12 tons of copper. The energy which is stored in a single beam is like 360 megajoules, which is equivalent to 90 kilogram of TNT or 15 kilograms of chocolate, okay? So if somebody likes chocolate, one has to really worry about, okay, how much chocolate one consumes. The amount of liquid helium in the machine is 60 tons or something like 120,000 gallons. LHC is the coldest place within the solar system with a temperature at 1.9 degree Kelvin. It is also the emptiest space in the solar system with the vacuum in the pipe containing the beams at 10 to the power minus 13 atmosphere. Now, you need a very fine camera to observe the things which come out. So this is one such camera, which is called the compact muon solenoid detector. This is the detector where I work on. Okay, I mean, obviously, okay, I mean, I cannot work alone. Okay, I mean, such a thing I cannot build alone. I mean, no country can build alone, and even it is not built by a single continent. So it has got a total weight of 14,000 tons. It has got an overall diameter of 15 meters. And when I say the overall length is about 28.7 meters, this is, I would say, this is the central part of the detector. We have detectors which are 140 meters away from the interaction point. And just before coming here, okay, I mean, I was working on the detector which was 140 meters away from this interaction point. This is called 0-degree calorimeter. So CMS is the heaviest particle physics detector ever built. It is twice as heavy as the Eiffel Tower and 800 times as dense. The solenoid of the CMS is the most powerful magnet of its kind ever built. It generates a magnetic field which is 100,000 times stronger than that of the Earth, and it has got stored the energy which can melt 18 tons of gold. The tracker we have various parts of the detector. We have just surrounding the interaction point, you can see what is written as a pixels and tracker. That is a detector which is the fairly empty detector. It hardly interacts with the particles which comes out, so that you can see the trajectories of charged particles in those parts of the detector, that's why it is called a tracker. It is surrounded by, it obviously does not see the neutral particles, and we have to see the neutral particles. So surrounding the tracker, we have got something where the neutral, the photons which come out will interact and deposit all the energy. So this is called electromagnetic calorimeter. So beyond that, okay, some of the hadrons which come out from this interaction will obviously interact a little bit with this electromagnetic calorimeter, but many of them aren't not fully absorbed in that. So we have something which is called hadron calorimeter, which has built out of coppers, and I'll come to that, okay, I mean, in a minute. And after that, okay, the only particles which are escape are muons or non-interacting particles like neutrino or something totally unseen, okay, so which maybe, okay, I mean, some things which can be candidates for some dark matter objects. So we have a tracker which uses essentially silicon sensors, which covers an area with the size of a tennis court with 6,000 connections per square centimeter. Then we have electromagnetic calorimeter, which contains 86% metal, is lead or tungsten, but is completely transparent. The observer of the hadron calorimeter uses brass cases of over 1 million World War II shells at the Russian Navy. So you can see, okay, this was the picture before the hadron calorimeter was built. These are essentially those brass cells for the coming from the Second World War, and they were casted and made into the hadron calorimeter detector. So this is how a particle which comes out from this interaction traverses through this detector. As I said, only the charged particles, which has got a very large electromagnetic cross sections, they ionizes the empty gases or come in or deposits the energy in the silicon detectors. This is the tracker. If it is a photon or electron, then they are totally absorbed in the next layer of detector, which is the electromagnetic calorimeter. And then comes the hadron calorimeter who come in where all the charged hadrons are observed. And finally, the particles then leave the magnet coil, which is a superconducting magnet, as I said, and it again traverses through the layers of detectors which are again detects charged particles, which are the muon detector. So that's how we can identify charged hadrons, neutral hadrons, electrons, photons, and muons. And obviously, if you try to, we have some prejudices in high energy physics that we have prejudices like we have got momentum conservation and energy conservation. So if you measure the total energy of the total momentum, and if there is an imbalance, okay, we can say, okay, there's other particles, neutral particles, which has escaped the detector that could be emitting energy. Now, the LHC, when it started, okay, I mean, it was operating, it was giving a luminosity, okay, which is essentially the number of events which is per unit cross section, and that was fairly low. Okay, so in the first phase, you have got something at the level of picobarn inverse of cross section. Then we went to something like 6 femtobarn inverse cross section, and then we went femtobarn inverse luminosity, and finally, when it was really successful, it went to something like 25 femtobarn inverse of integrated luminosity. And obviously, when it was have a low luminosity run, we have got only few particles, something like, okay, I mean, you have got 2 interactions per when the bunch crosses each other. So it is the top picture over here. So here we can clearly distinguish between the particles which is produced. This has become a little bit worse. You have got 10 interactions per bunch crossing, and then finally, okay, in 2012, we have got 20 interactions per bunch crossing. Then I think, okay, we have gotten now to, we are happy if there are only 40 interactions per bunch crossing, but we are nearly working with something like 60 interactions per bunch crossing right now, and it will be 140 to 200 in coming future. So how much data are produced? We are trying to produce, okay, I mean, fairly large number of data. Okay, nearly you get 1 gigabyte of data in every second. So we collect something like 15 petabyte of data per year in the early days, and now we are collecting even more data per year. It's enough to fill a hard drive in 2 minutes, and you can process. The thing is, okay, if you try to collect them on CD stacks, the height of the stack would be something like 20 kilometers. So you can see, okay, I mean, obviously, okay, a Concorde flies only 15 kilometers above the surface of the Earth. Okay, so we have got a CD stack, okay, much larger than at what level, okay, a Concorde flies. Obviously, we cannot analyze all this data in a single laboratory, even if we have got one of the biggest computers, okay, I mean, in the world, okay, at CERN. So we have to process it all around the world, and we have to develop something which is called a computing read, okay, by which, okay, we can really analyze the things all over the world. Now, why, if you have such a complex system, how can we believe, okay, anything which just comes out? So obviously, when the collision started, we have to see, okay, from the detector, evidence of already known particles. We have, so far, in thing, okay, which has got discoveries of the muons, the pi meson, the kaons. Then we have got the various, hyperons like lambda, sigma, cascade, and so on and so forth. Then the discovery of JSI, discovery of the B quark, discovery of W and Z bosons, and discovery of top quark. This happened, okay, in the year 1933, all the way up to 1995, over the year of 62 years. Now, we have the first collision in December 2009, and from December 2009 to July 2010, in the course of 6 months, we saw evidence of the all these particles, and then we see, okay, I mean, this particular detector is essentially rediscovered all the standard model particles. So we believe, okay, that the way the detector performs and the way we analyze the detector is acceptable. After that, we, I think in 2011 only, we started seeing events like this. This is one event in the CMS detector where you can see a large energy deposit, this blue, what you call, trapezoids, which are there. Okay, this is essentially say that this is a high energy deposits in the electromagnetic calorimeter, so, and there's nothing in the tracking detector. So this may be, okay, I mean, something, a candidate event for Higgs going to a pair of photons. Also, there are evidence of events like this. Again, I am seeing evidence from the CMS detector where you have got two traces of particles going up to the muon system with sufficiently high energy, and also two charged particles having large energy deposits in the electromagnetic calorimeter. So this is evidence of Higgs going to 4 leptons. 2 of them are of electron type and 2 of them are muon type. So we start seeing those objects, but start seeing objects is not good enough. We have to establish that beyond some statistical accuracy that we are really seeing something over background. Every experiment, okay, whatever you do, okay, I mean, there is always something like a noise which is there. So we have to find evidence that we are not seeing something which is already expected from our standard knowledge of physics, but something excess to that. So during 2012, CMS along with ATLAS announced the discovery of a new particle. It has now been shown that this new particle has the properties of the standard model Higgs boson. That means it decays either to pair of photons or 4 leptons. And if you look at the statistical accuracy, the accuracy is of a background really showing such an excess is 1 in 10 to the power 6. That means 1 in a million, and all is called is a 5 sigma effect. So obviously, okay, this was in 2012. And so this was a picture in July 4, 2012, where this one gentleman and a lady, okay, I mean, they're trying to present their results. The gentleman is representing the CMS experiment, and the lady representing the ATLAS experiment. And they're looking upwards. They're not looking at the sky. They're looking at a picture which is also, because this particular conference was, this particular presentation was made at CERN amphitheater, and it was broadcasted also the same time in the I-Shape conference which is happening in Melbourne. So they're looking at the picture where this set of gentlemen, okay, sitting in the Melbourne conference, okay, I mean, were trying to thank, okay, I mean, and doing at this result. I happened to be at Melbourne attending this conference at the time, okay, so I was part of this particular audience, okay, I mean, trying to see, okay, these results. So obviously, this was not just the high energy physicists of the world, okay, I mean, who were celebrating this. This came up in the papers all over the world in almost every language, including Bengali. And obviously, okay, I mean, we have a celebration whatsoever. Now, in the year 2013, the the Nobel Prize in Physics was announced, and these two gentlemen, okay, who are sitting down below, okay, Engler on the left-hand side and Peter Higgs on the right-hand side, they were awarded the Nobel Prize on Physics for the discovery of the Higgs boson. They predicted the Higgs boson in '64, and it took us something like about 50 odd years, okay, it's 48 years, okay, to find them out. So it was a long journey, okay, for doing things. So when you are trying to do something, trying to prove an experimental for doing that. So obviously, this is to summarize. In 2012, the two experiments operating at the Large Hadron Collider provided a very strong evidence of a new particle with a mass around 125 to 126 GeV. The observed properties of this new particle are broadly consistent with the standard model predictions of the Higgs boson. And obviously, these studies drew the attention of people all over the world. And such a thing could happen only through international collaborations of thousands of people working over 2 decades. And this is a picture of The Economist. Even that, okay, it says a giant leap for science. But we are not idle, okay, for the last 10, 12 years. We are still studying the properties of the Higgs boson. And one of the things which is there is that we are trying to relate, okay, the coupling of the Higgs boson to the fundamental particles and trying to see, okay, the correlation of this thing, okay, you can see it is a power law relationship. It is a log-log plot, and it is a straight line in a log-log plot. And this is the situation. The left-hand plot is what we have seen so far, and the right-hand plot is a projection what we'll see in another 10 years' time. So with that, I just want to end my talk. Thank you.
Are there any questions? We can have 1 or 2 quick questions.
Well, it's great that you saw the Higgs boson. Of course, you got the Nobel Prize for that. But we knew pretty much it had to be there. There's no way that it could not be there because of the 18, 17 had been seen. And this was the last element of a puzzle. And furthermore, it was Fermilab which almost saw it. Yes, I know it didn't see it, but certainly the limits were there. And so it had to be there. It's not the case with supersymmetry. Supersymmetry, we don't know how it's broken. We don't have any limits on the masses of the particles either, except very wide ones. So what's your comment on that? The difficulty of seeing SUSIs as compared to the difficulty of seeing the Higgs.
Can I comment on this? The thing is, okay, when Indian group were trying to be a participant of the experiment, I think, okay, there was a group of so-called, the guys who try to come and say, okay, are you doing the right experiment or not? I had to present it in TIFR, okay, on behalf of a accelerator-based experiment. And I said at the time, okay, finding Higgs or not finding Higgs are equally important because there are multiple of models which are around which can give rise to the masses of this particle without a Higgs mechanism. Higgs mechanism is the simplest mechanism to give the mass of this particle, but this simple mechanism may not be the right thing, okay, for the things. So I think even at the beginning of the experiment, we could be even more excited if we did not find the Higgs boson in the LHC experiment. So that is one thing. What is the other thing which you mentioned? Okay, the best limits of the Higgs boson came not from Fermilab, it came from the LEP experiment. LEP experiment really tried to observe this Higgs boson right from a mass of 0 to up to the mass of 114 GeV. And they could not find it, and they put a limit from 0 to 114 GeV from the LEP experiment. In Fermilab experiment, they tried to look for the Higgs boson, and they could only look for the Higgs bosons in a limited mass window between 145 to 160 GeV. So that was a region, okay, which was covered by the Tevatron experiment. It so happened, okay, I mean, I worked at both Fermilab as well as CERN, and I can say, okay, I mean, I may be a little bit biased towards CERN, okay, but I think, okay, I mean, the amount of work which was done on Higgs boson at CERN is much more than what was done at Fermilab at that time. Okay. Obviously, okay, I mean, I said, okay, I mean, I showed a picture of something when you do not give an address and try to find for it. It is not an easy job, okay, I mean, try to find for it. We have been trying to look for supersymmetry for a long time. I think, again, LEP was the first experiment, okay, which tries to look for very low mass supersymmetry. And obviously for supersymmetry, there are, I do not know, okay, maybe 1,000 or million, I do not know in what order of models, okay, which are there. There are many models which exist in supersymmetry. And in some of the supersymmetric model, obviously we could rule out the existence of supersymmetry up to a certain mass. Obviously we cannot rule out supersymmetry in all models. So some of the supersymmetric models give rise to such a small cross-section. I mean, this cannot be reached by any of the experiments which has been done so far. And if it is a very very standard type of supersymmetric models which is around, we can reach only up to the range of about TeV, okay, I mean, in the Large Hadron Collider so far. If you want to go beyond, obviously the best way of going beyond anything, okay, is to increase the energy. If you want to increase the energy, obviously you have to either build a larger collider or build a much stronger magnet which can bend the protons or antiprotons, okay, in the 27 kilometer. This is the largest tunnel which exists, is a 27 kilometer long tunnel. So either you have to build a bigger collider in size, or you build a stronger magnet so that you can increase the energy by a factor of 2. This is in the horizon. Now, I have been working in this CMS experiment for more than 30 years. And if somebody can say, okay, I mean, can work on this experiment for the next 50 years, okay, they may say supersymmetry. But one needs patience, one needs dedication, and one has to work, okay, day and night, okay, for doing this thing. And you may not get it.
I think, thanks. In view of the lateness of the hour, maybe we should have the discussions later. So let's thank Sunand. Yeah.
Hello. You, at the end of your talk, you tried to say that how much luminosity do we require and how much we have achieved about the luminosity.
Maybe you could just keep it short.
The conclusion that you talked about, we have come up to this much of luminosity. We need How much luminosity you require to finalize the whole thing?
No, I think, okay, I mean, obviously, okay, you cannot instantaneous luminosity at which we can operate is, the design was something like 10 to the power 34
Yeah.
per centimeter square per second. We are operating now at 2 times 10 to the power 34 per centimeters per second. And we have what you call a high luminosity LHC, which will operate at 10 to the power 35 per centimeters per second, and it will run for another 15 years. That means in 2041. So that we can have, right now we have accumulated somewhere around 300 femtobarn inverse of integrated luminosity, and we have to increase it by a factor of 10 so that you have at least 3000 femtobarn inverse or 3 at autobarn inverse, and maybe something around 4 autobarn inverse as well. So that was the current design, okay, I mean current, what do you call, scope of the collider.
Okay, thank you.
Let's thank Sunanda for a nice talk. And the last talk of the day is by Punyabrata Pradhan, and he will talk about anomalous fluctuations in systems with a broken time reversal symmetry and center of mass conservation.
ফুল স্ক্রিন ফুল স্ক্রিনটা কি করে করবো? থ্যাংক ইউ।
So it's a great pleasure to be here, and thanks to all the organizers, especially Professor Kamrul Hassan, for kind invitation. So I see a bit depleted structure in the audience. So all of us are tired. Computer little while ago went to sleep mode. Probably you are also in that mode, including myself. Okay, so today the story is how do you go to the sleep mode? Not quite. We take a simple model, which is our statistical mechanical physicists say favorite model, and talk about the quote unquote sleeping mode of a system. Okay, so this talk will be based on these 3 recent references. One got published recently in this year, the other one last year, and one in the archive. So today I'll not talk about any elementary particles like bosons. Rather, I will talk about some emergent properties of matter. So what is that? If you are Brown and looking through microscope and observing colloidal particles, so that's the thing. Source Wikipedia. So now you see, I mean, lot of small things are going around. So now you ask this question. You take, so you have a big system, and you take a small subsystem of, say, length L. So then you ask, what will be the variance of particle number in that subsystem? Well, the particles are going out and coming in because they are colliding and they are doing some random motion. Well, at the large volume limit, large subsystem size volume limit, so that follows expectedly a central limit kind of theorem and the variance of particle numbers. So you take n square, like n is the particle number, minus n average square, so that is the variance. And how it goes as a function of that system size L. Well, central limit theorem says it should be proportional to the L to the power D, goes as volume in the large volume limit. Well, so that's here. So we talk about mass fluctuation like particle fluctuations. And small L is the size of the subsystem. And your system is quite large, say infinitely large. Okay, so in principle, it may go as L to the power lambda into D. D is the dimension of the system, and lambda is certain exponent. So lambda equal to 1, we see normal fluctuation, like Gaussian-like fluctuations according to central limit theorem. Well, when lambda greater than 1, okay, so that we call giant fluctuation. So we don't see it often. You take a equilibrium system and tune, say, temperature or say magnetic field, and you hit the critical point, like say water and vapor critical point. And there you see huge fluctuations. And there is a nice experiment on that. That's called critical opalescence. Okay, so that's our favorite equilibrium physicist critical phenomena where lambda greater than 1. So now we ask whether lambda can be less than 1. So less than 1 means suppressed. So we are very quiet, almost like sleeping mode. And we'll ask, how can we approach such systems, say dynamical origin of that thing? How do we approach that kind of systems? Okay, so for that, since we like to calculate fluctuation property, so our favorite thing is current fluctuations. So, well, you can talk about other quantities too. Okay, so in my talk, I'll confine myself to mass and current fluctuation. Okay, say you take, say, some time integrated quantity. So now, when you talk about, say, particle number fluctuations, you take, say, a big subsystem, no? It's a space integrated quantity. So now you add up certain quantity on time. Say you certain activity at, say, 1 second, after 2 seconds you measure another activity, you add them up like, say, 10 seconds, 100 seconds, million seconds, okay? And so that's the QIT. So QIT is nothing but our current at a particular space point I, or say ith bond in your favorite model system, and you measure current up till time t, right? How many particles flow, say, through a surface, so back and forth, in a time window t. So since an additive quantity, normal fluctuation will give you that variance must go as t. But is that the case, we ask? Okay, so, and in that context, there is a recent paper in EPL 2018 by Garcia Millan et al. So they talk about dynamic hyperuniformity. So they actually did not study current fluctuations. They study some other fluctuations, which is called activities. So that sounds also a relevant quantity. And they found it's a very quiet system, and they characterize it numerically. Okay, so one thing is that, so suppressed fluctuation actually indicator of some non-trivial correlations, and it can be actually long-ranged. Okay, in this context, so this model Sandpile is quite old model, 89 or 88, I think, 1988, by Bach-Tang Wiesenfeld. So they introduced this model to explain the long-range correlation in nature. Like, avalanches are going on, and certain other things, and mountain ranges, they are very irregular. And they have actually found to have long-range correlations, like, or say, I don't know, luminosity fluctuation in solar flare, something like that, some exotic stuff. And they thought that they had a grand sort of model, although it is not true probably. Well, but their model was quite nice, which is called Sandpiles. So it's our favorite model, a very simple model, which will come to it. And that Sandpile model, people studied in last 30 years, but in last decade, so 2015, they found that model, which has which is called fixed energy Sandpile. So there is one conserved quantity, which is the particle numbers. And you tune particle numbers, and suddenly you see below a certain critical value, system becomes very, very quiet. And at the critical point, which is the below that value, rho c, no? So it's quiet. So which is called absorbing state. It's like dead state. You go into it and you never come back. Literally we dead. I mean, so we know, all of us, we know that we may be dead at some point, but still we are going on with our activities. So the system is like that. Okay, so now in this talk I will elucidate the role of conserved quantities in these systems, or getting these exotic kind of systems which have hyper-uniform fluctuations. It is called hyper-uniformity. Okay, so there is another, so maybe I will take some bit longer time on introduction. So whenever you give me some warning, so I will go to the conclusion. So motivation is important. Well, so some apparently different context. Another exotic quantum systems like fractonic fluids, so studied by Shenoy and Moisner, 2020. So there they found that the excitations, you create say two particles, no? Say, I mean, but they cannot move independently. So there are certain constants they should satisfy. One simpler, I mean, I thought simplest example is this: a system which has charge conservation as well as dipole moment conservation. So dipole moment conservation introducing one extra conserved quantity. And what they found, well, things are actually quiet, and they characterized it through slightly different quantities. What they said, well, if you say create some perturbation, so then how that relaxes? Well, they found they relaxes very, very slowly. Well, but how slow it is? Well, they are subdiffusive. So they are not like Brownian particles. No, diffuse and spread like square root t or something, the displacement, but they are not like that. They are much slower than that. Okay. So they thought that, when you introduce this extra conserved quantity, which actually gives you certain constant, that particles are not independent. So if I move in this direction, so the other particle must move in the other direction to you can say that center of mass is conserved. To say it slightly differently. Okay, but is that generic? So now that we found that, so that's our thing, what we claim, is that no, it is not generic. Actually, it is very, very details dependent. You change the details, things are quiet, but this characterization actually is not unique. Okay, so what we found is that when we break, so they studied the model which has time reversal symmetry. But if you break time reversal symmetry, situation is different. You break some other thing, you introduce some little bit change, things can be different. So there is no general statement. So that's our thing, one thing. The other thing is that, so how the fluctuation, how you characterize the fluctuation, current fluctuation, which I think that that's a bit new thing. So this is the our framework in nutshell. So we see air, but you see, to derive the the governing physics of air molecules, which is, I guess, Navier-Stokes equation. But if you start with microscopic models, it's actually very difficult to. If you start with say standard model string theory, you are gone. But well, we are statistical physicists are very modest. So we start with some very simple toy model. Even then, it's difficult. Why? Because if the particles are interacting, to get the coarse grain description is not easy. Why it is not? I will come to it. So then, so it's a kind of diffusion equation, but non-linear diffusion. So it's a density diffusing, but with some diffusion, two transport coefficients. One is diffusivity, which is density dependent, and another one is that fluctuation, which is actually a current fluctuation. It's a conservation, so it satisfies continuity equation because density is conserved. So that that's called actually mobility, the chi. Okay, it's like conductivity only. Okay, so now we would like to characterize these two quantities in certain model context, which is called sandpiles. So we consider two models, Oslo and Mana models. We study density relaxation and the current correlation functions and their power spectra, as well as static structure factor. So what we find is that the properties actually depend on details. Density relaxation need not always be subdiffusive. However, current fluctuations are much more suppressed than observed in the diffusive system having a single conservation law. Okay, so that's the model. Well, so this is a threshold activated kind of model systems, which is the particle can hop if there is, say certain things crosses certain values. So in this model, what it says that if mass at a particular site is greater than 2, greater than equal to 2, that site will be called active, and a particle or two particles or multiple particles can hop from that site. If the number of particles at site, say, is less than 2, so then it does nothing. So it's kind of absorbing. So that's a locally absorbing state. I think the model is very simple. And particles with active, active sites, they topple with rate 1. So that's the model. Okay. The second model is that Oslo model. So in the previous model, particles, when one site throws a particle, so the particles can hop independently, left or right. But in the next model, conserved mass Oslo model, there is another conservation law. When a particle moves, the other particle must always move in the opposite direction to keep the center of mass conserved. So that's the extra conservation law we put into the system, and we like to say theoretically study fluctuations. Okay. Okay. So we actually we have been able to do some analytic calculation. So these models, one thing is that their steady state properties are unknown, because they actually violate detail balance, and the steady state, they do not follow Boltzmann-Gibbs distribution. So that is not known. That is one thing. The other thing is that if you want to calculate various correlation functions of certain order, say you want to calculate evolution of density, so then you find that density will depend on the 2-point correlation, the higher order correlation. If you want to find say evolution of 2-point correlation, that will depend on say 3-point or 4-point. So it's called BBGKY hierarchy. So that's actually a formidable hierarchy, and that's actually the main problem of statistical physics of interacting systems. How to solve that hierarchy? And it turns out it cannot. In most cases, you cannot. So in this case, what we thought is that, so let me skip this one. Thought is that, well, what is the nature of the current? So earlier side, I can come back to it. We showed that the things are diffusive. You see, particles, on average, there is no current. No, one particle is going on the right, the other particle, on average, going to the right, left in both the models. Okay? So you can expect that the motions are diffusive. No? Okay, so assuming that, so we say, well, large scale structure of current must be like this, that. Let me explain a bit. So this is the current operator for the random variable, and you want to calculate current correlation at 2 different times and 2 different positions. Well, so that's a time evolution equation. Right hand side, you discover another operator which is called diffusion operator for this model, so which is called activity. So left hand side Q involves some other operator. So now we'll have to calculate the evolution of the other correlation functions A and Q, and you encounter another operator. It goes on. So you cannot solve this hierarchy. So now we say, first we identify what is that operator, and in this model it turns out that operator actually is a diffusion current, which is in the red we have written. So if that's the diffusion current, it must be proportional to a diffusive, say, mass gradient, Mi, and the nearest neighbor site, Mi plus 1, and their difference, times diffusivity, which is the effective diffusivity. Well, with that, you put that in 12, and then you break that hierarchy. So then you get the equations involving only 2-point correlations, which you can solve. And since things are diffusive, you immediately know, so we'll have to kind of couple diffusion equation. That's it. And which we solved. Okay, so that's the thing I skip, and that's the solution. See, current correlations truncated, so means I have subtracted the average value. And right hand side, you get something. Well, it's a diffusion equation. You solve it, you kind of get e to the power minus something. which is the relaxing mode, right? I mean, and diffusion is the relaxation rate, basically, inverse rather. And certain coefficient, which we identify. So the point is that if you calculate current correlations, you find an integral like q square e to the power minus q square, and which will immediately give you t to the power minus 3/3. So this is known in the context of diffusive system with single conservation law. So now you see what happens in our case. Here you get, instead of q square, another q square. But what is this q square? Well, q square is nothing but the diffusive current. You see, your system is of order L, so q is the long wavelength, it's 1 by L, so current is of order 1 by L, so that's the diffusive current. And that mode, so it contributing current of order q square, and that mode relaxing with rate e to the power minus q square, you sum over it and you get current correlation. Here another q square comes from the fact is that it comes from the structure factor. So which is that in this case, when you put an extra conserved quantity, so it becomes actually compressible. So the current correlation is something like q square times particle fluctuation. That makes sense, right? I mean, when particle will fluctuate, it will contribute to current. But in this model, particles are actually fluctuating, but they are fluctuating very coordinated manner, so that they becomes actually very incompressible. In other sense, the structure factor actually vanishes. Okay, so then you do this asymptotic and you get another behavior t to the power minus 5/2. So I believe that this is a new result, and so that's the role of conservation here. Although this system is perfectly diffusion, I mean, like Brownian particle in the first slide, like what Brown saw. But, well, of course, Brown did not see the system with a coordinated movement, but if you see that, you find that. Okay? And it does not depend on other things, I guess. Okay, so how much time do I have? 10 minutes. Okay, so let me explain this plot. So this is for Manna model, one sample, which has only one conserved quantity. But I told you that below certain critical density, things become very quiet. Well, then what happens at critical point? So now, say, if I plot q square t, which is a cumulative current across a particular bond in a time window t. So how it will happen? Well, you say that, well, at very large time. So it's like uncorrelated things, no? I mean, so then q square, so square of sum of random variables will go as t. And that's actually happened. Large time it goes as t. But there is a bit of a story here. So this t, but the coefficient is actually very small. So in the thermodynamic limit, that t part goes away. So I'm not explaining in detail, but that's the thing. That's the typical behavior in a particular system. Okay, so now what happens in thermodynamic limit, what we see that t to the power half kind of behavior crosses over. And that's the behavior, so half, so it actually goes as t to the power half. It's not t. So its system is sort of hyper uniform in time domain, which we call dynamic hyper uniformity. Okay, so now this is the case. Now what will happen to the other system? So other system, of course, it's very constrained. So it will be more suppressed. Because here you see one particle going to this direction and another particle going to the other direction. So, I mean, it's like, say if you talk about a subsystem, say if you talk a subsystem and you calculate the space integrated current, it will be 0. But in other model, the Manna model, which has one conserved quantity, it is not. So you see current, I mean, it's very suppressed, and the correlation function also says that, no, the decay of the current correlation is much faster than the systems which have only one conserved quantity. Okay, so that's the result. It's a bit complicated slide, but I would like to ask you to only refer to t to the power minus 3/2, which is, according to our calculation, far away from criticality. And in fact, this model, the calculation is actually approximate. No, assuming that things are diffusive and large scale, certain operator you can represent approximately some other operator within approximate. But there are other models where actually you can exactly calculate this within this framework, like having a system having two conserved quantities, and so fortunately they do not have a structure like that BBGK hierarchy. So that's the certain advantage, and you can exactly solve it. So that's in the archive. Okay, and the relevant power spectra is this, and say, well, so that's it. I will not go into further detail. Well, now say, what happens in the Oslo model? So Oslo model, what I told you that since there is a coordinated movement, yes. So quite surprisingly, Q square T at long times, it just doesn't grow. I mean, I found it quite remarkable. Well, I mean, I'd appreciate if you have any comments at the end of the talks, but it doesn't grow due to that very, very coordinated movement. So it actually saturates to that sigma square, and the correction term also we calculated with some within this our approximate calculation scheme, actually which agrees quite well with the simulation result at the left. Of course, this doesn't work near criticality. Based near criticality, this calculation scheme breaks down. Okay, this is more complicated. So my student actually prepared this slide. I forgot what it is, but anyway, it's in the paper, so you can look at it. And I'm there for another 3 days. So t to the power minus 5/2, and you see the green line at the tail, and the asymptotic is the black dotted line, which is the top left. Black dotted line is our theory within this approximation, and the green line is simulation. So and the theory is reasonably good, I guess, with the t to the power minus 5/2. Okay, and within that truncation scheme, one could also calculate the structure factor, which actually goes as Q square. It is very, very suppressed. Okay. So I think I should conclude. So we study the one-dimensional model, Oslo model, a prototype for many particle systems undergoing absorbing phase transition and having multiple mass and center of mass conservation. We compare our results with MANA model having only one mass conservation. Density relaxation, which is actually diffusive, which I did not tell you about. There are certain anomalies at critical point which you can imagine. So which actually can be, even though there are certain constraints, it can be super diffusive too. That's very counterintuitive. Okay, instead of sub-diffusive, it can be actually super diffusive. Okay, we discovered this unequal time current correlation function has this power law tail t to the power minus 5/2, which is much faster than t to the power minus 3/2 in a diffusive system which you observe, which has a single conservation law. And the static structure factor, which goes as Q square, so it's called a very extreme kind of hyperuniformity. But in the Oslo model, at criticality, it is less hyperuniform. In the MANA model, it's actually opposite. Away from criticality, it has normal fluctuation, but at critical point, it has abnormal, in the sense, hyperuniform fluctuations. And there are reasons for it. So with that, okay, I would like to acknowledge these guys, Professor Deepak Dhar, S.S. Manna, my colleague, and Salvatore Torquato, he's at Princeton. So with that, thank you very much for your attention.
Are there any questions?
I'm sorry, this is going to be dumb questions. So let me apologize for that.
No. There is nothing like
it is
that.
because of my ignorance, I must confess. For example, when you actually mentioned, because I'm not very much familiar with experimental methods that much, so that's why my questions might be dumb. So when you refer to criticality, let's say, for example, in equilibrium statistical mechanics, we have certain kind of criticalities, and you actually can do measurements from which you can actually see these scaling behaviors near the critical points. As far as these time-dependent things are concerned, how do you actually measure them? And specifically, since you are working with one-dimensional models, there ought to be some kind of a experimental measurement.
That's standard. Actually,
Standard may be to
no.
you.
So you measure relaxation rates, like say Ising model. You at the critical point, you say, I don't know, experimentally what you do, but theoretically, I guess you just flip few spins and you see how it relaxes.
I mean, I can do it in VS simulations. I was just wondering whether there are.
No, there are. It's actually called critical slowdown. So there is a huge literature.
No, I know about critical slowdown when you actually try to do simulations towards second order phase transition. This is what happens. I was asking, are there any physical systems? If I want to do something in the lab, take for example, not on the computer.
Yeah, I think scattering experiment you can do. Yeah.
Okay, that's one. And the second thing I was actually curious about is this: when you actually mention these fracton models that you have. So, for example, when you have charge conservation.
I do be dumb. I mean, I don't know much, but you please carry.
Oh, no, then we're on equal wavelength, so that's not a problem. And I'm sure if there are others who are actually cognizant of these things, could you help us? They could help us here.
Sorry,
which
this
is,
one, fractonic.
Yeah. So the question I had, take for example, if you're dealing with like charge conservation, that follows from a gauge principle. So if you have a U1 gauge theory, you will actually get, out of Gauss law, you will get a charge conservation. So as far as these fractal models are concerned, you actually have higher moments of charges.
Right. Higher moments are conserved.
So in that case, would you, I mean, how this, can be phrased in terms of like new type of gauge theories that you can do on fractal models?
No, one could, but I don't know.
Okay, thank you.
Are there any other questions?
So you had this fat tail.
Yeah.
So what is the significance? Is it something to do with the rare event? Something like
No,
that?
fat tails, it comes from the conservation laws. See, because there are slow modes, like, diffusing mode, it takes a long time to die. So that's the reason. You have a conservation law, and there will be fat tails.
In that case, if you do the cumulative distribution, perhaps the fat tail will go away and you can get a better estimate of the exponent.
No, current actually has two parts. So that's a good question. So, yeah. You see, I see. Okay, so current, so when you write down say, coarse grain equation, so there are colloidal particles, on average, say it's a diffusion, like you create a gradient, the particle will flow, but there are fluctuations. So there are actually two things to current. One is the hydrodynamic mode, that's a slow diffusion. The other is the fast mode, fast fluctuations. So that's why you can write down this Langevin type of equation, no? And it has certain properties that noise and fluctuation, relaxation, they have certain kind of relations which called fluctuation dissipation theorem. So you consider slow modes, they will have fat tails. But if you subtract that part from the actual current, then actually you have that short range that is very much well behaved. And that's why you can actually develop your theory.
Are there any further questions? If not, let's thank the speaker. Let's thank both the speakers.
So with that, we are finishing the day one of the conference, and tomorrow we will start again at 9 a.m., but a different venue, and that is the, Nawab Ali Chaudhuri Senate Bhavan, Dhaka University. So, so that is actually inside the Dhaka University campus. And for foreign guests, our volunteers will pick you up from the hotel and take you to the venue. So if you have any questions, you can ask, or in that case, we will finish our today's session. Thank you. Thank you very much.